Dun dun dun. Okay, so here is the character movement project, the first project for the GPE class. Alright, so GP 340, the Milestone 1, root motion. Okay, so character uses root motion, character moves north, south, east, west. Character rotates to face the mouse, tap down camera tracks player via code. Character uses rigid body and colliders, seen as appropriate for testing. Okay, so we're going to go ahead and cover all those in one fell swoop. So for starters, let's go ahead and click on our player pawn. And ba-ding, there's the capsule collider, and ba-ding, there's the rigid body. Okay, so that's this one. So character uses root motion. Character uses root motion. Character uses root motion. Apply root motion right there. It's not the way that it sets the stuff up is that you have the you have the animators up here, and as you can see, as was shown in class, you have the blend trees. And my only addition to the blend tree is what we covered on Tuesday's class with the dodge state. And you can see the entry commands for entering into the dodge. And the dodge effect just has the additional parameter of the trigger for the dodge effect. That's it. Code-wise, you could just implement that by adding in the dodge effect. And all mine does is a jump. And if I had to write it for game lore, I'd just say it makes the player, puts the player out of phase with reality for a brief second, which allows projectiles to go through them. Which in truth is just going to change the opacity of the character to like 50%, and it's going to turn off the collider box for like 10 seconds. It's going to turn off the collider box and the gravity for the character itself, and then turn it back on afterwards, so that they can dodge projectiles trying to go through them. Really not complex. Explain parameters sent to the animator. Okay, in order to explain the parameters sent to the animator, the animator is pretty straightforward. It has forward and right. To get any deeper, we actually have to go to the blend tree here. And all it's going to do for the blend tree, as you can see here, the additional features that I added for the animator is I have the walk state, I have the run state, and I have the sprint state. And you can see them positioned around the character in the cardinal directions, the 8 cardinals. And I have the idle state, which you can't see because currently the motion controls are right on top of it. But slide this forward, it tries to move right. Slide this forward, it tries to move strafes. I found out that having the multiple move states and the multiple blend states, what that predominantly does for me is it makes the transitions smoother between a walk to run to run to sprint, so that the gradients of the motion for the interpolation of the various animations is a lot smoother the more movement nodes you have. And that's just really helpful for making it look better, which we'll see when I actually hit the play button and have it move. But yeah, up here is the real key part, because this is what decides how fast the motions are and what the maximum, and ultimately what the maximum y value and minimum y value can be, and what the maximum x and the minimum x can be for the inputs. Because if it doesn't have an input map to it, it doesn't animate, or there's no animation. And the value that you can input to this can only be as big as the maximum number or minimum number, or small. Negative numbers are confusing. Strong X, small x, or left and right. Really, because it's Cartesian, it's just better to think of it as left and right when it comes to animation than to think of it as a positive value or a negative value, even though left is a negative in comparison to center, somehow. Um, but yeah, other than that, the rigid body, one of the things that I figured out with the rigid body is kinematic in order to make it so that the animator is what's moving it. And then collision, the interpolation and the collision detection. I figured out that continuous speculative and extrapolation are the best choices because that not only, it's not necessarily that it keeps my character from falling through the ground, just the capsule collider itself does that. But with the extrapolation and the continuous speculative, it provides the least amount of catching on the train, since I'm actually using a train object for the testing field instead of just a regular flat square. So the nice thing about train is that with train I can actually change the physics material for it, so I can make a certain area slippery, or I can make it, give it elevation. That the elevation and the shape of it's going to come from train data. The actual physics of it's going to become coming from material, which I haven't loaded one yet. But yeah, back to the character. So my input controller is really simple. Like really, really simple. I did not attempt to do anything complex, advanced, or funky with it. So one of the things that I do right off the bat is I declare three private vectors: goes yonder, begets yonder, and begets to cinder. So begets yonder, I'm using the inverse transform direction for vector 3 forward, so I'm passing in the global vector for forward into the transform for the character itself. The input controller is probably not going to stay on the character itself at the final form, but as of right now, this is the most ideal method for transforming the character controller and everything else. Aside from this, I'd probably pull the transform for the pawn itself into like the input controller on the empty object itself before I do any of the calculations. But as of right now, I'm just pulling the transform from the character itself, and I'm doing an inverse transform direction in order to get begets yonder, which is itself a vector 3. I could have probably just popped it into float, but in order to receive it directly from the inverse transform direction, it actually has to itself be a vector 3. It's just the way it is. Then with begets yonder, I actually pull the z from that in order to multiply it against the z of the input, which is, how it moves left to right. And then I have the x, which is up and down, visually. Oh, or well, technically I guess this one is up and down, because y goes like this, x goes like this, and z goes like this. So, Tusender is going to be my left and right, and yonder is going to be my up and down, or forward and back. And then what I do is I pull the current input from the vertical and horizontal inputs, and that's a float. So that just goes directly into the private floats that I have up here. And then I pull the get right, or the goes right, from that, which is the horizontal. And I multiply the goes up against the transformation for it. So it asks, okay, what is your right direction of the transform? And then it creates a vector which represents the delta, or the different direction for the mutation, or the not necessarily mutation, but it if my character is pointing this way, then its forward is going to be along this axis. So then what it does is yonder is my final input, or my final vector. So what this does is it multiplies the controller inputs and aligns them so that irregardless of what direction I'm pushing, if I'm pushing left and the character is facing down, the character still moves left. Instead of moving to its left, it moves to my left, the way that I'm looking at it globally. Another way to do this would be able to make it move against the camera, but we're not doing the move against the camera. We're doing a move against a fixed global position, because I just wanted to use the global camera position instead of this is just using the global position. But another way to do this would be to offset it against the camera's direction, the direction that the camera's pointing. It's perceived global, which would be an extended, really just an extended equation in here that uses the camera instead of the global. And it would actually pass its transform into this, then transform that into that, so we'd know which way relatively to the camera that the player was moving, that the player's character was moving, instead of just which way relatively to the world position that the player is moving. And this is like kind of mind screwy camera controls, but it works. Yeah, so it turns local. It finds out what what forward would be for the pawn itself, and what right would be for the pawn itself, and then it multiplies that against the inputs in order to determine which direction the pawn is actually going to end up going. But yeah. Okay, so then here's the look at mouse. I put them in separate scripts because I could. This one's really simple. It just casts a ray at a plane. It casts the ray at the plane in front of the camera, x distance. It's just using vector 3.up, vector 3.0. So it's just casting it at a 0 level. And then it's going to go ahead and produce the empty variable for distance, and then that accepts the output of the plane.raycast method. And then what that goes ahead and does is it will do vector3 target equals ray.getPoint distance. That actually gets the point where it hits instead of just the distance of where it was hitting. Distance, since it's just a float, just says, okay, it's this far away. And then getPoint will tell us, okay, where is that point? Which is kind of necessary due to the fact that in order for it to then get a direction, get a vector of a direction, it actually has to take the target, which is the vector 3, which you get from the ray.getPoint method by passing in the distance. And then it goes ahead and converts that into a vector. And then this turns that wonderful radians into actual degrees so that it can be used in the Euler. And then transform.rotation equal quantirean.euler 0, rotation, 0. And since I intend to use an Xbox control, after this I'm going to have a switch statement, or case. It's going to be a case statement that uses switch, so that if I'm using a controller, it uses the right thumbstick in order to determine which vector that the player character is going to be looking at, instead of using the raycast. because, well, I could make like a game, like I could make a crosshairs element for it to look at, like it moves around a game object in the world as a crosshair, and that the player would look at that game object or turn to face that game object. I feel it would be better if I just used the thumbstick to point the character in a direction rather than moving around an object, because then my character can only turn as quickly as I move the game object, and it's kind of hard to find a balance for those. But with a top-down shooter, the two joystick method is tried and true. So you can move your player in one direction while pointing it in another. And by just relying on the direction that the thumbstick, that the right thumbstick, the look thumbstick, is pointing, to change which direction the player is pointing, allows for a far more intuitive and reflexive and responsive character control than if I was just going to move around a game empty that had like a crosshairs on it. Because then I'd have to control the speed of that, I'd have to control the motion of that, I'd have to put in a bunch of script to control how it moves around, to limit where it can go on the screen, and it's just nonsense. It would be clunky, it would be hazardous, it would be hard to execute, and then it would also interfere with gameplay. And I really don't want it interfering with gameplay. So the mechanic of just being able to tap the right thumbstick to change which direction the player is pointing seems to be, to me, to be a far more intuitive way of dealing with the character controls for gameplay than if I was using a game object to get the character pointed around. But hey, that's just me. Okay, so let's see. Character uses root motion. I've explained that. So use of it, explained how it works. Okay, move towards. Okay, so yeah, I'll go ahead and explain that. Appropriate for testing, explain that. Well, I'll show it during the plane. Well commented / well named / variable scope. Well, as you can see, this thing literally just has two private variables. There is nothing externally that it needs to declare as a part of the class that it can't just get from the globals that already exist. Camera.main.screen.point_array, input.mouse position. It just pulls that. And, well, it creates that on the instance that in the instant that it needs it. So, yeah, I don't, these three are contained within the update function itself. So that's as far and as long as they exist. And these vector3s and this float only exist within the if statement itself. They don't exist outside of it. Fun. But yeah, other than that, the mouse position only exists as a private up in here for the sake of ease. The last angle only exists up there for the sake of ease. And it only really does that for the sake of later implementation for when I'm doing look at angles and everything else. This gets pulled during the initial startup of this class, or of the object the class is attached to. And these just exist inside of the update function itself here. So yeah, the scope on those is very tight. The rest of the scripts. Here's the camera chase. There's another way to do this, which I used in previous projects, but Vector3 Move Towards is a lot simpler, more straightforward than the other ones. The only thing that I'm really doing with this is that I use the offset position in order to determine I use the offset position in order to keep the player from going up, in order to keep the camera from going up the player pawn wireframe, to basically keep it from trying to insert itself into the base of the player pawn. And that really just only exists here. I could probably move this up here, but it doesn't really matter right now, because it's not like it's keeping very much track of where everything needs to be. I could probably move this down here for move rate equals 60 times time dot delta time, but it's just fine where it is. It doesn't necessarily need time dot delta time. It only does that because this allows me to scale it depending on how complex the scene is during the initial startup. And this one's kind of interesting because it just does transform.position equals player character dot transform dot position. So initially when we start up the camera, it's going to have the same transform as the player pawn, and then this goes ahead and offsets it down here. But the main reason that I redo the offset each and every time is because I add it to the player character dot transform dot position. And what that allows me to do is when I put it down here, it goes ahead and this is where it's currently at. And this is the offset position. So the offset position is this added to the current place where the player pawn is. And then this is where the camera currently is. So then it attempts to move from this position to the offset position at this move rate, which is right here. And it ends up for being a very smooth follow camera. That's pretty much all of my code. I really did not write a lot of code for this one. So the only three I really used were input controller, look at mouse, and player chase. And player chase is on my player chase camera. And look at mouse and input controller are both on the pawn itself. And yeah, that's all the code. It was really not a coding intensive project, though it took me a lot of trial and error to get to that point. Okay. You can't see it on the keyboard, but when I press up, the player moves in the direction of its localized, or of my localized up. So when I press W, it moves up. When I press down, it moves down. When it's facing away from when it's facing my mouse pointer and my mouse pointer is under it and I'm pressing up, it's still moving up. So I'll point the camera at it. So I'm pressing down, it's moving down, even though that's normally forward for it. And when I press W, it's moving up. It's going backwards and moving up, even though that's normally back for it. For my classmates, I apologize, but the professor will get what I'm saying with this. I press D, which is typically it's moving to the right. It's moving to its left, while I'm pressing the right movement. And now it's moving to its right while I'm pressing the left movement, because of the orientation that it's currently facing is getting translated against the global, so that it moves in the direction of the direction key I'm pressing, rather than moving along its local axis. It's moving along the global axis of the input, rather than moving along its local axis of the input. Yeah, I know. It hurts my head too. But Obviously, in order to demonstrate that, I have to have it be able to look at the mouse. This will work better once I implement the joysticks because it doesn't like accepting multiple keyboard inputs simultaneously. That could also be solved though uh, by pulling by assigning an actual 8-directional compass rose input instead of just the 4 key inputs, and it'll also be solved when I integrate the Xbox One controller into the controlling scheme instead of just having It was actually easier to push these around before I implemented the inverse control scheme. So as you can see, the speed of the character will also vary depending on which direction the mouse is pushing, or which direction the mouse is pointing. Because let's say this one. If I tell it to move backwards, it has one speed. If I tell it to move forwards, it's actually faster going forwards than it is going backwards. And here we can see the walk speed. And then let's see if I can, yep. This is that's almost the run speed. That is about the run speed. As you can see here, because of the way that I set up the input controllers, you actually have a greater variety of movement transitions than if I had just had 2. So you can actually see the interpolation gradients in action. And then left shift is going to be the dodge roll, which I'm not going to use directly. But the other thing that I did was, since this is a terrain, implementing the terrain and getting it working with all the colliders and everything else was more than a little bit of a chore. But as you can see here, I have even these boxes set up with rigid bodies and colliders so that I can push them around as world physics objects. Do. And there we go. So that is my presentation. I'm going to quickly cover how I implemented the train and go from there. So train is a Unity object. It's really convenient because you can assign a single collider to the entirety of your train. You can also do a ton of stuff with decoration and design for trains, and it's very simple to change like the tags on train and the globals on train. So if you want to check if something's grounded or if something's within a certain specific spot, checking it against terrain instead of hand building it out of a bunch of different 3D or 2D objects is a lot easier than going ahead. It's a lot easier to use terrain than it is to build everything out of primitives. So since most of the game industry actually uses terrain rather than hand building their levels out of primitives, I feel this is actually going to get me further ahead on developing terrain and terrain colliders than if I was just going to build levels out of primitives. I think terrain is pretty cool. Before I finish this project, I intend to get some hands-on experience on using water shaders and using water as part of the level, not necessarily as an element of gameplay, but as an aesthetic. One of the things that I want to do with this game while I'm building it is I'm going to generate towers that emit particles in rhythm to a certain portion of music tracks. And I feel that's going to provide a certain amount of visual hook and visual aesthetic to the gameplay. With the top-down shooter, I'm already shopping for the projectile effects and the special effects that'll go along with like hits, destructions, stuff like that. I intend to polish this piece not only to the point where it would happily be a part of a professional portfolio, but to the point where it could be published and sold for money. Because I feel that if I want to really market myself as a game developer, as a game programmer, that I should work towards making a releasable product so that people can see how I'm able to bring stuff together. And Unity assets are really going to be helpful for developing a game on a budget and being able to develop a game myself, just myself, as a game programmer. So yeah, physics objects are kind of cool. Um, if I want to make these explodey barrels, I would just use the undestroy command, and I would swap them out for like blown up, burnt up uh, polys or three-dimensional shapes of after they explode, and I'd make a sound and kaboomy particle effect on their destruction, and then after X amount of time, the replacement shapes, the destroyed barrel sections, which would swap out for this with its alignment and array orientation, would fade away or dissolve after a certain amount of time. Um, but yeah, that's pretty much it. So the dodge roll for the top-down shooter is being included because it pretty much just exists for the large majority of the top-down shooters or the top-down brawlers or anything else. The ability to dodge out of the way or dodge out of the corner is just kind of something that I've become very synonymously aware of when it comes down to bullet hells. So including that is pretty much just sticking with industry standards. I'll probably include other special features other than just like graphical design and appearance as I'm developing the game, but the dodge roll is just like the dodge jump dodge roll is just like in my mind absolutely necessary for a video game of the top-down shooter style. So other than that, I think that is pretty much going to cover everything. The new mechanic for me is train. That is above and beyond what was required. Uh, train for me is just such an amazing, fantastic, new, awesome thing. But in entirety, with like the animator and everything that comes off the animator, this just feels like such an advancement because now I've gone from making the little asteroid ship zip around the screen to animating a 3D model and making it do things that I see constantly in the third person shooters, first person shooters, and everything else. So to me, reaching this point makes me feel like I've arrived at being a developer for modern games. And modern games use terrain. There's just no two ways about it. So since this is a modern game and I'm using animations on figures and objects in that game, I felt like if that's the bread, then train's the butter. Thank you for your time.